Okay, well, I guess we'll get started. Is this working? Yes? No? Is this working? Now it's working. Okay, good. So this is joint work with Vi Hart, who sadly isn't here. Well, so first let me introduce or remind you about symmetry, because what I'm talking about is symmetry groups. So symmetry of an object is a motion that leaves the object looking the same. So this very simple design here, if you rotate it in one of 4 different angles or you leave it the same, then nothing happens. So it doesn't change the look of it. And so you get a group by, well, so you can add together symmetries, you can combine them by rotating by different angles. And so the group is the set of objects. Do I say this? Yes. The group is the set of symmetries of an object. In this case, you can rotate by 2 pi over 5, 2 times 2 pi over 5, and so on. And there are 5 elements, and you can combine them together to find others. So here's another example. Presumably everybody knows the symmetry group of this. So we again have rotations, and we also have reflections. So there are 4 rotations you can do, including the do-nothing identity element. And there are 4 reflections for a total of 8 elements. And the symmetry group is D4, or perhaps sometimes called D8, depending on your notation, the dihedral group. And so these show up a lot in artwork, of course. But groups are studied independently of symmetries of physical objects. So, groups have been classified. The finite groups are now possibly entirely classified. So you can ask which of these groups appear as sculptures or as objects in nature. So which groups can be represented as the group of symmetries of some real-world object? And so this is, in a sense, this is a little bit of a fuzzy question. There are many sort of issues here. Well, first of all, again, what do I mean by symmetry? I specifically mean there's some motion of some space which takes the object onto itself again. That's what I mean by symmetry, some isometry of the space, if you like. But there's lots of issues with this question. Real-world physical objects are made of atoms. Is there actually any truly symmetrical object where all of the atoms are actually in exactly the same place after you rotate them? Probably not. Anyway, here's a second question. Which groups have actually been represented as the group of symmetries of some real-world object? So just think about rotation groups. You can rotate by some angle. Your group is the cyclic group of order n. There is some n which hasn't been done, just because there's infinitely many n's and there's only finitely many things in the world. And the third question, which groups have been represented as the group of symmetries of some physical object here at Bridges 2014? So I spent the last few days going around trying to answer that question in a sense. So first of all, some of the bilateral symmetry, just reflection, the group is C2. Perhaps if there's time at the end, we can go back and we can go through these and we can ask, spot the symmetry group. Where was this? Does anybody recognize this one? Yes? Cedric Villani's brooch. Here's the problem with, is this a real-world symmetry? Well, so the legs are not quite symmetrical, but if we can imagine that, well, it's sort of symmetrical. I mean, you can imagine that perhaps the artist was doing this just for an effect, but we can think of it as being straightened out and having actually symmetrical legs, of course, the museum itself. There are many cyclic symmetries throughout Bridges. The Best in Show winner here. This was another one from this morning. This is from the dance math show. Anybody know where this was from?
The drum.
The drum, it was the drum. They also appear on the subways. So these are, here's another issue. So does this count as rotation of order 2? Do you count the colors or not? If you don't count the colors, then it does. But if you do count the colors, then it has no symmetry at all. So these are the symmetries up to, cyclic symmetries up to order 4. Here are the higher ones. So Carlo had a symmetry group order 5, another one this I think is Mike Naylor's, 6, 6, 7, 8. This one was a little tricky to get. Does anybody recognize it? It's the big yellow thing, and if you look down from above, then that's what you see. 9, this one I think I counted as 17, and this one is 19? 19, yes, okay. Well, so there's the question. You didn't know you were participating in this competition, but you were. What is the largest symmetry group represented at Bridges 2014?
Largest in terms of elements?
Say again?
Largest in terms of total elements?
In terms of total elements, yes.
A5 plus...
Well, first of all, I have to say the largest finite, because, there are circles everywhere, so, but that doesn't count. Well, it's my talk, so I get to make some judgments here. This is what I think is the largest symmetry group. This was Mike Naylor's. If you set the Mark Naylor's piece in the show with the runes, if you set the number to 1 and the number of dots to 360, then there are 360 dots around here. Probably can't see this, so this symmetry group is obviously representing D360. However, you may say that the symmetry group of the 120 cell is more. Well, we'll get onto that one. The dihedral groups, so dihedral group of order 2. Here's a subtle one. Is this dihedral order 4 or order 2? The coloring's a little tricky. 3, 3, 3 again. This is 4, 4, 5. Where was this?
Dinner hall.
It was the ceiling of the dinner hall. This was a photograph on one of the stalls. Dihedral group of order 16, I think, doesn't beat Mike Naylor's 360 though. Which symmetry group wins Bridges 2014? Which appeared the most? What's your guess? True, yeah. Boring. Well, so, it's probably bilateral, people's faces, but more interesting than that, the dodecahedral reflection group is everywhere here. They're all over the place. Oh, actually, I made a mistake. This one is rotation. If you look at the words up here, you just see there's a word here and a word here. That's actually rotational symmetry. But okay, so there were at least, well, I only took photos of 10 of them, but I only have so much time. The dodecahedral rotation group also made a strong showing. There are many examples of that. Yet another dodecahedral reflection group, and perhaps you should say that this is really illustrating the four-dimensional symmetry group with 14,400 elements. Here's another dodecahedral rotation group from earlier in this session. I'm afraid I didn't get any photographs from Neri's lecture because I just didn't have time. But there were many, many symmetries there as well. The other polyhedral groups, this one's interesting. I think, if we imagine this as continuing on after it embeds in here, then this is the sort of cubic reflection group. And, well, there are many others. The wallpaper groups, not so many showings here, it must be said. There's a few of these around. And then some other interesting miscellaneous. These are not quite dihedral because you have reflections of this and also another way to do the sort of the dihedral flip. And these are somehow, I take these to mean that you can translate upwards or you can rotate and reflect and so on. So these don't quite fit into the other categories. And then there's various ones which are sort of showing hyperbolic things. And this is another sort of interesting point. These symmetries, clearly you're supposed to think of all of these heptagons as being the same, even though those are not Euclidean transformations, right? So we allow, apparently, not just sort of Euclidean translations as being part of our symmetries. And you'll have to ask Yoshi what is going on with this one. I think it's hyperbolic, but there's some complications and some branch points. And I'm sorry?
It's not hyperbolic.
You say it's not?
It's just whatever you see, you get whatever you see.
Well, but can I think of extending this onwards? No. But this is yours, and I'm thinking of extending this onwards. What's the difference? Anyway, look, we can talk later. And then, right, so are these are showing four-dimensional symmetry groups. I think probably we have to say that that's true. So maybe this should have won after all. But anyway, moving on. The real question I want to ask, are there any glaring gaps? Are there any small groups that should have a physical representation as a symmetric object that don't? As far as I know, the Quaternion group, so this is an 8-element group that I'll describe, has never had a physical representation, but it's only got 8 elements. I mean, why not? So to get at this, to describe the Quaternion group, I'm going to get to it by looking at these very simple monkey blocks. This is Weihart's invention as a way to think about these things. So I've got a block. It has, it's just a cube which has patterns on the sides. So there are 2 monkey faces, 2 monkey paws, and 2 monkey tails. And these all have handedness. And so we fold this up into a cube like this, and this is what you get. So the 2 faces are opposite each other, as are the 2 paws and the 2 tails. Something to notice is that all of the faces, the hand faces, the tail faces, and the face faces, have handedness. So, and they're all opposite each other. So this is a left monkey paw, and this is a right monkey paw. The tongue is sticking out to the left and to the right, and the question mark tail twists in different directions. And so this cube itself has no symmetry whatsoever. It looks like it might do, but there's just nothing there. And so your question is, how can you fit these together so that the faces match? And so the first thing that you might think of is just stacking, say, the paws together. So here, because I've got a left monkey paw on one side and a right monkey paw on the other side, if I sort of swap the order, if I take a copy and stack it next to the other one, then they match together. And so you can make an infinite line of these monkey blocks. And so the first question, what are the symmetries of this infinite line of blocks? Anybody? What is the symmetry of this infinite line of blocks? Say again?
These groups?
Well, so I can translate, that's certainly true. This guy is the same as this guy, and it's going to repeat after every 4. And so I can just translate 4 blocks along. Oh, Craig is making the right hand gestures.
90-degree screw rotation.
90-degree screw rotation, left-handed, I believe. You would not imagine how much of a pain it was to figure out the handedness of the screw rotation. So yeah, so what is going on is you go from this to this, and the cube screws left-handed rotation as it goes. And so you get the integers. I can also think of well, since it repeats after 4, I can imagine just wrapping it around and having only 4 blocks which are twisted around like this. And then the symmetries are 90-degree screw rotation, but it's going around in a circle. So you screw around, you move. So these arrows here are supposed to, unintentional puns of a sort. Isn't that what we're all doing all the time anyway? So you rotate this ring of blocks around, and you also twist by 90 degrees as well. And so this has a cyclic group of order 4. And you can also stack them vertically. So it turns out that you can't sort of take this infinite row of blocks and stack just to make a wall. It doesn't work. You can see, so there's a line of 3 blocks through here, and then you put one up here, and then there's no block that can fit in this gap here. But I'm sure some of you have already realized, given the shape that I've got on the screen here, that what you can do is you can, if you could close up these 2 faces so that 3 cubes fit around one edge, then it all works and everything matches up and you get a hypercube. So we have to move to 4 dimensions, and 8 of these monkey blocks glue together to make the cells of a hypercube. So this is a complicated image. So this is the net of the hypercube exploded, showing all of the different left-hand screw motions through those rings of 4 blocks. So I've got, let's see, there's a ring of 4 blocks going along here through the tails, and then there's another sort of dual ring of 4 blocks going through here, again through the tails. And so you can act on this configuration of cubes by doing both of those tail screw rotations at the same time, and that's a symmetry of the object. And it's the same thing with the K and the J. So what is the group of this object? There are 8 symmetries. Well, so how do you know there are 8 symmetries? Well, So one cube on its own has no symmetries itself. If you're going to have a symmetry of the whole object, you have to move a cube. You can't just have one sit there and do something. And that cube can move to any of the other 7 cubes, and so there are a total of 8 different symmetries, and you can just work it out. They correspond to the 8 elements of the Quaternion group. So this is, has 8 elements. It's 1, ijk, minus 1, minus I, minus j, minus k. And these are sort of, it's an extension of the complex numbers to 4 dimensions. So 1 is the do-nothing element. I, j, and k are these 3 screw motions. Minus I, minus j, and minus k are the going in reverse screw motions. And minus 1 sends every cube to its antipodal opposite. And these satisfy the relations that you expect from the Quaternions. If you're not familiar with the Quaternions, there you go, that's what they do. And so these really show you what is going on with the Quaternion group. So how do we make a sculpture which has this symmetry? So each monkey block itself has no symmetry. And so we want to, or rather it has only the do-nothing symmetry, being pedantic. So if we want to make a sculpture that has this Q8 symmetry, we have to put a design which has no symmetry into each cube of the hypercube. So if you put something which had more than no symmetry, or only the trivial symmetry, then your eventual object would have too much symmetry. So you want exactly Q8, you have to have no symmetry in here. So obviously it should be a monkey, because monkeys are the canonical choice for objects that have no symmetry. Once you move the arms around a little bit, okay, why is it a monkey? So you put copies of it into the other cubes. You need whatever the design is to connect into this through to the 6 neighboring cubes of one cube, and a monkey has a tail and 4 limbs and a head, so it's the only choice. It's sort of tricky. If you're going to have something that has no symmetry, what do you do? I mean, I guess you do something figurative, because there's no restrictions otherwise, so why not? So how do you draw 4-dimensional pictures in 3-dimensional space? I talked about this 2 years ago at Towson. Just a brief recap. So this is a picture of stereographic projection from the 2-dimensional sphere to the 2-dimensional plane. So there's a light up here which is projecting rays of light down onto the plane, and so a line goes from the light source at the north pole of the sphere. It hits the sphere once and it hits the plane once, and the map just is what is the point on the sphere, and that maps to what is the point on the plane. So how do you get so if you're going to do this from 2-dimensional sphere, sorry, this is the 2-dimensional sphere. It may look 3-dimensional, but it's a surface, so we would call it a 2-dimensional sphere. So how do you get a hypercube? Well, in this case, we're going to do a cube. How are we going to map a cube onto the 2-dimensional plane? So first, we radially project it onto the sphere. So this is a sort of hard picture to see, but there's a cube here sitting inside of a sort of rounded cube, and you can see the shadows coming from the light. This is radial projection onto the sphere. And then we do stereographic projection again from this sort of beach ball rounded cube onto the plane. And if you do the same thing 1 dimension up, projecting the hypercube radially onto the 3-sphere, the sphere in 4-dimensional space, and then stereographically projecting, it's exactly the same mathematics, into 3 space, then this is what you get. And if you do this with the monkey design, then this is what you get. More fun than a hypercube of monkeys. I should mention Will Segham, my brother, designed the monkey because he knows how to design things that aren't math. And I think that is pretty much my talk. Is there anything else I wanted to say? That's it. Thanks very much. Are there any questions? Yeah.
When you mentioned the symmetries of the Quaternions, and you said you map one to another one, it's determined. Is there an intuition for why you can't choose the mapping of the others?
Let's go back. Maybe you can repeat your question, because I'm not sure I followed you.
You said there's 8 symmetries because once you put one cube somewhere, that determines everything.
Oh, yeah. Well, so I guess the question is there any choice in how you glue the cubes together? If you've determined the shape, the position of one of them, right, I mean, gosh. Right, I mean, I think the point is that once you've decided where one of them is going to go, then all of the gluings to determine where the other ones you've already done. So, I mean, you have to be ungluing, then regluing things to get a different object. Maybe? Maybe we'll try and figure it out afterwards. Yes?
Yeah, very nice. I was wondering about this monkey. I mean, certainly he wasn't hurt because this is all in S3.
Right.
But your brother, did he design the monkey in the first place?
No. He designed the monkey in this cube. So I wrote a little program that he could, just a command line script that he could use to see what happened to the monkey as he was tweaking things, and it would give him back the distorted stereographically projects version. It's sort of tricky. You have, how are the hand and the tail going to wrap around each other? You have to sort of keep designing it and going back and forth and seeing what the effect of doing some sort of change here in the Euclidean cube has in the original, in the final picture. So it was a little bit tricky. But he's kind of obsessive, like I am. So, yeah.
How satisfactory do you find this solution? Maybe as a follow-up question, using similar techniques, would you not be able to just create objects for any group?
Right. So there is some distortion in the eventual object, right? I mean, so we get to here. So this object itself has no symmetries in R3 if you just allow Euclidean motions. But in the same way, I think, as I was very careful to say that Vladimir really is showing hyperbolic translations, but those aren't Euclidean transformations either. But we interpret them as being symmetries of that object. So, right, I mean, there's some hand waving here. I mean, this isn't a very precise question, but yeah, I mean, I think it's reasonable to say that this shows enough to allow the viewer to infer what is going on. And particularly with the animation, I think that helps as well. As for the question, can you now do everything? It's not at all obvious to me how you would do that. And so I'm specifically saying, a symmetry is a motion, right, it's an isometry of some geometric space. So how do you do that in general? And how do you represent it effectively in 3 dimensions? If you want to take the monster group, 168,000 something dimensional object, is there any way to produce some thing which is
Well, we only need to produce a visualization.
Hold on. So there's an issue here. How much time do we have? Plenty. So there's an issue here. So you could say, why don't we just draw the Cayley graph? You can draw the Cayley graph of everything. I agree. And so, yes, that is a way of visually representing the group. You could argue so is just writing down the presentation. That is a way to visually represent the group. I want to see sort of visual motion that I can imagine doing, which acts on the object and leaves it looking the same. So I mean, it's an aesthetic choice. I guess we can argue about whether or not this counts or not. But. Hello. Another question?
I was a bit surprised that you start with the cube and the faces of the cube, because you know already that the group acts on the hypercube. So basically,
you mean in
construction with the dual, basically, construction of faces is the one you do for the dual. The dual is again the cube. So.
I'm not sure I quite followed.
In a cube.
Yes.
And you have these faces and mirror images. And
yes.
do that thing together.
Right.
So the graph that you then get when you go through the faces.
Oh, is the 16 cell.
This space of the dual
of the hypercube.
Of the cube, which also happens the cube.
That is
So you have the
true.
acting on the cube, and then you have to do the mirror image stuff, which is, I believe, the semi-direct product of Z2 and Z4, something like that.
Maybe. So the dual of the hypercube is the 16 cell, which is a...
No, I'm not saying the dual. I'm saying you start with your construction
Right.
of the cube. It's probably nicer to see, picture of the monkey.
Right, right.
You probably start the construction.
Oh, in the dual cube.
Well, then you would have an image on each of the corners.
Right, you'd have a... it would be rather violent to the monkey. It would be cut up and there'd be an eighth of a monkey here and an eighth of the monkey there.
That's right, so you imagine the centers of the cubes in the heart of the monkey.
I see.
You to move the...
Well, designing the monkey itself is harder to do if you cut it up into 8 pieces. I mean, yeah. Right. There are already difficulties with, the hand had to be cut off and then put on the other side and then stitched back together again. And yeah, I mean, already the design is kind of tricky, even with the connections that there are. Any other questions? All right, well, thank you very much again.